All right, so thinking about our system, something that we're going to do in order to calibrate our data later is collect a metal plate calibration. So that means taking a 4x4 piece of metal. It doesn't really matter what type of metal it is. So something light is probably ideal. So you're not having to slog this 4x4 metal plate around that's really heavy. You're going to place it under the antenna and collect a file that we will use later in Radan. We used to have people jump on the bumper to create this calibration file to simulate how the antenna would be different levels from the ground during actual collection as the vehicle's bouncing. Our engineer, Roger Roberts, found out that that's not actually necessary. We always end up with this linear relation, regardless of whether we've done the bumper jump or not. So you don't have to do the bumper jump if you don't want to. But anyway, we take this metal plate cal file into Radan and we create this short calibration file. The idea behind collecting this antenna cal file on the metal plate is that we are calculating the maximum velocity and amplitude that our radar energy can possibly move. We are just shooting it through air into a perfect reflector. So we're going to get the fastest and strongest reflection that we can possibly get from our system. This then gets compared to all of the scans in our data in order to calibrate their velocity, which allows us to set our depth up correctly. The math for that is here. So we're comparing our metal plate reflection strength to the pavement reflection and the velocity of the air we know. And so this is complicated math happening behind the scenes. And it's actually not even the full math because the equation here doesn't assume the distance between our transmitter and receiver. It assumes that it's shooting from the same element straight down to the ground. So this is just an idea of kind of the math behind it, but it's actually a little more complicated. But that's what we're doing with this metal plate cal. We are calibrating our data for velocity and for depth. It doesn't matter if you do this at the beginning of the day or the end of the day. I would say if you end up collecting two like that, just pick whichever one you think is more representative of the bulk of your collection. Or like the end of the day, use the end of the day one. If it was more like the beginning of the day, use the beginning of the day one. Theoretically, it could. I personally haven't witnessed a large scale change due to factors like that. But theoretically, yes. Given how kind of quick and easy it is to collect the metal plate cal file, I would say just do it again because it only takes a second and it's pretty easy. On the actual SIR30 interface, there's a button along the bottom that says metal plate calibration. All you have to do is click that button. So if you already have the system up and running, it takes like 30 seconds to do that. So yeah, if you find that the weather has really changed throughout the day, it might be worth it to collect one at the end of the day. And another note with that, do not collect data while it's actively raining. One, because the safety of the system, we don't want water getting into the antennas. Two, if there's a lot of surface water on the top of the road and a lot of puddles and things like that, you're going to get a big reflection of energy off of the water sitting on top of the surface, which means there's going to be less energy to actually go through into the subsurface. So your data quality is not going to be as good. You won't get as much depth penetration, and it's dangerous for the system. So try and do it on drier days. So salt is going to increase the conductivity of the ground surface, which is going to kind of obliterate your signal. So also if it's been recently salted, I would err against collecting any data. So this is something probably for in the warmer months to be doing. And I know some folks kind of spend all summer collecting data and then process in the winter, but up to you how you want to approach it. So we collect this metal plate cal file. In Radan, we turn that into our smaller calibration file with the file type .czt. We can then open our data file, which will look something like this. And in our raw data, we're seeing the direct coupling at the top of the profile. So that's the reflection just from the bottom of our antenna. We're then getting our surface reflection, this kind of brighter layer here. This is air in between our direct wave and our surface reflection. And then we're getting some reflections from sublayers here. Because we want to understand the depths of all of our layers, we need this ground surface reflection to actually get bumped up to the top of our profile, so it's at 0. So to do so, we can use our antenna calibration file. That's going to go through and do all of this math and adjust each scan individually to snap that layer up to the top of our profile so we can start looking at our layer depths. So we're going from something like this at the top to something like this below. So this really bright reflection now is right at the top, straightened to 0. So we can visualize all the layers below. So we'll go through doing this in Radan. Once we have that calibrated, we can go through and start picking all of our layers. You can also, as this notes, if you have cores that you're already collecting, we can integrate that core data and we can export all of this information to CSV, which you can bring into any other number of inputs that you may have. You can process 2 channels at once. So in this case, we've got 2 gig data and 400 megahertz data. It looks like this might be another 2 gig. So you can do your layer picks and we'll see that in the depth pane below here. We can also, if you collected with GPS, see your GPS path. And when we're exporting our data, there's a number of fields that we can choose from depending on what you're interested in. What you select for RoadScan is going to be a little different from what you would select for bridge scan. They're interested in different things. So I'll talk about the different outputs for those. And then this is an example of what that Google Earth export is going to look like. So you can see the scale here on the left. So anything in red is showing a depth of between 1 and 1.75. Anything in the yellow range is 2.5 to 3.25 inches deep. So you can see the different kind of variations along this roadway. And we'll create one of these. And here's just another example of that. And you can use this information if you complete like a network level analysis. You can use this information to decide what areas to go back to and maybe do some additional testing. It can help you point out problem areas.